Hey there everybody. I've been wanting to do a series of videos for a while on different technology stacks, and I figured a good place to start was with paradigms. So a paradigm is kind of a really high level way to structure a program or to use a certain program or programming language. Um, there's different paradigms for different types of programming, and usually a paradigm is designed specifically to fill a need or something that the designers felt was lacked in a different paradigm. So kind of the first paradigm was imperative. Now imperative is where you give a series of instructions that can be fed directly to a CPU or a GPU or something like that. They're usually pretty cryptic looking. Here's some MIPS assembly code, for example. So this first one here is saying load word, which is how you extract data directly from a memory address on your stack or heap, and then it's saying save it into a specific register, which is directly controlled by your processor, and saying load another word from this offset from this memory pointer and is stored in this register, and then here we're adding whatever's in this T0 register with whatever's in this 0, which is always 0, and store it over here in this one. So anyways, this isn't an actual program, it's just a couple of instructions that I threw in there. It's been a long time since I've written any assembly code. But it kind of gives you an example of what assembly looks like and what this imperative programming style looks like. You give commands that are directly given to whatever processing unit you're using, and the processing unit can directly interpret each of those and do something with it, which allows for some really great control of your processing unit, but is kind of tedious to write. You see all these T1 and T3 registers, and you kind of have to keep track of it, and there's not really a good naming system, and it it can get really confusing really fast, and it takes a lot of commands to just it takes these 3 commands just to add numbers up. And so you can see it can be pretty labor intensive writing stuff in assembly, and they have written some really amazing programs and still do write some pretty amazing programs in assembly when they really need to get down to the nitty gritty. But some really smart people over in Bell Labs, I believe it was, came up with this idea to abstract away from assembly code, and that kind of leads us to our next one, which is structured programming, and I'm going to use C as an example of that. So the structured paradigm is essentially you create a list of commands that a compiler will then take and turn into assembly code. So it's a little bit cleaner. You can see these are a little bit nicer. It's probably a little bit more familiar looking to most of you. So what happens is I give it a set of commands, so this int right here, x equals 0, then goes to a compiler, and the compiler turns it into a series of commands that look something similar to this. And it still allows you to control really closely what the processing unit is doing, but it makes it a little easier to read, makes it a little bit more human friendly, and so you can write bigger programs more efficiently and with slightly less chance of bugs, maybe, depending on your skill level, but it's a layer of abstraction. So this is structured, which is an abstraction of imperative, and the next one I want to talk about is declarative. So there's a couple different declarative programming languages. SQL is probably the one that you're most familiar with if you've done some significant programming. So SQL is all based off of set theory. So set theory has kind of 2 trains of thought that go into declarative programming, such as SQL. So SQL is a relational calculus, And relational calculus means that it says exactly what needs to happen, but it does not say how it needs to happen. There is an underlying relational algebra that can specify exactly how something needs to happen. So there's this really amazing proof that was written that shows that with a pretty high degree of certainty you can prove that using a base set of relational algebra and relational calculus, any query that you write in relational calculus can be directly translated into a relational algebra that can be turned into computer code eventually that is exactly the same as what you put in your calculus. So some really, really interesting stuff there, and I imagine that we will go into SQL sometime in the future just because I use it all the time and I think it's wonderful. So the next paradigm is this idea of object-oriented. So we could go into hours and hours and hours of any one of these paradigms, but just to give you a quick overview of what object-oriented is, as they were writing these structured programming languages, they realized that there wasn't a really good way to collect the data and the functionality that accompanied that data together. So what they did was, I'm not 100% sure, but I think Smalltalk was one of the first object-oriented programming languages, and Java and C++ were kind of based off of that same mindset. So I have a really, really simple little Java program here, just prints hello world. But you can see up here we define a class, and we have this data, this number integer that we never use, and then inside we have a actual function that just prints out hello world to the console. So object-oriented programming allows for some really awesome structures that make larger programs and make handling programs a lot easier in certain aspects. So definitely some really good ideas there in object-oriented programming, a lot of wonderful uses. So functional is kind of a cool one. It is based off of the idea that everything should be a function, as it's called, and there should not be any side effects. So one of the slowest things in programming is making calls and reads to and from memory, because the memory clock cycle is so much slower than a CPU clock cycle. Going and querying or writing something into memory is really slow, and also side effects are more difficult to mathematically prove. So functional programming languages, sometimes you can actually mathematically prove the correctness of your program with functional programs. So Haskell is kind of my example for this one. I really, really like Haskell. I think it's very interesting. To be honest, I've never used it for anything outside of just learning Haskell. I've done quite a bit of functional programming. Usually I just use the functional programming in Python or the functional aspects of Java or something like that. But Haskell's great. I think everybody should learn it just so that you understand how functional programming works at a very pure level. So this first little snippet here I have on line 2 is a compilable Haskell snippet, and it will print out the first 11 odd numbers. So this is list concatenation. It follows very closely to like a mathematical set theory list concatenation or list generation formula. So the second one is another list concatenation, mostly just because that's what I've used Haskell for, so I'm most familiar with it. And it says, okay, given this number xs, if I save it to x, and then I say if x is odd and x is greater than 100, then print the word large, or else print the word small. So it's kind of dumb, doesn't really do anything, but It's a really interesting programming language, and it all comes with the idea of everything should be a function. You notice we don't really do a whole lot of variable storage here. It's all very functional. It's based on creating a bunch of functions and grouping them together to make a program. The last one I want to talk about is logic programming or logical programming. So Prolog stands for programming logic, I believe, is this really interesting program. Um, Honestly, I kind of forgot how to write it. I haven't written it in a couple of years now. It is based off of the idea that you give it a bunch of rules and a bunch of facts, and then based off of that you can query, say, does this rule match this fact? Is this fact true? Are these facts true? Are any of these facts true? Are none of these facts true? Are exactly one of these facts true? And that kind of functionality lets you do some really interesting processing that is very difficult sometimes in other languages. Natural language processing is really interesting in Prolog and can be quite difficult in some other languages. So, like I said, that's just a really stereotypical overview of paradigms. We could go a lot more into these, and some of what I said isn't strictly true, but it's a good idea and it's a good example of how this stuff works. So hopefully as we discuss some of these in a little bit more detail, you can keep this high-level overview in your head to kind of help you reference back to. So I thank you for watching, and I hope to see you in our next videos.